Okay, shall we start? Where's the boss? Okay, wait for the boss. Okay, which is.
Yeah.
Shall we start?
You can start.
Okay.
Whenever you want.
Okay. Okay, so. So we'll continue where we left it the other day. So we finished with the ADM equations. So I'm going to write them again. Okay, and I'll write them in the ADM coordinates. Okay, so we use this covariant form in terms of the normal vector and so on. But let me just write them in the usual ADM coordinate, just to make explicit a couple of things. Okay, this is just the expanding the Lie derivative of the metric, of the induced metric with respect to the normal vector to the hypersurfaces and writing it out in terms of these ADM coordinates. Okay, and then after some long derivations, we use the Einstein equations to derive an evolution equation for the extrinsic curvature. So the equations that we got. May I close this? It's a bit noisy. So we got an equation again that was for the Lie derivative of the extrinsic curvature, and now I'm just expanding it in terms of these ADM coordinates. So that's just the same equation that we wrote the other day. And so these are the labs and the shift. The prime curvature is the Ricci tensor of the spatial hypersurfaces, and that's computed with respect to this induced metric. Okay, as you can see, these terms basically just come from expanding the Lie derivative, and this comes from the Einstein equations, and these are just the decomposition of the stress energy tensor. Okay, so these are the equations that we got the other day, and these equations allow us to evolve the induced metric and the extrinsic curvature. So we have to provide initial data. So the initial data is clearly the induced metric on, say, a t equals 0 hypersurface and the extrinsic curvature. But this initial data is not free. It has to satisfy the constraint equations. And constraints we've got the Hamiltonian constraint, which relates the Ricci scalar on the hypersurface and the extrinsic curvature. In terms of the, okay? And notice that this is, so the Ricci scalar has two derivatives of the induced metric, so that's an elliptic equation for the induced metric. And solutions to this equation, well, are non-trivial. So said in other words, so it's not guaranteed that there are solutions to this equation for all matter distributions, okay? signs here matter in terms of existence of solutions, but I will not go into this in these lectures. And then we have another equation, which is the momentum constraint. Okay, so these are the so-called ADM evolution equations. The first comment I want to make is that in these equations, so this is the whole content of the Einstein equations when we write them down in this ADM form. Okay, that's it. There's no more. So notice that in these equations, we've got the shift vector and the lapse function, and they appear, in particular the lapse function appears with second derivatives, and we have no equations for them. So this is a reflection of the fact that these variables, namely the lapse and the shift, are gauge, right? And this is also reflected in the fact that the Einstein constraints do not depend on the choice of lapse and shift. Okay, so the lapse and shift, what they represent is just give us the freedom in terms of how these t equals constant hypersurfaces are embedded into the full space-time. Okay, so in order to evolve these equations forward in time, we need to provide evolution equations for the lapse and the shift. And this is non-trivial. This is non-trivial for two reasons, because lapse and the shift represent the freedom to choose coordinates. You know that not all coordinates are good coordinates. So for example, in the Schwarzschild spacetime, the Schwarzschild coordinates are not good coordinates because they become singular at the horizon. So for the same reason, it's non-trivial to come up with evolution equations for the lapse and the shift such that they avoid coordinate singularities. And finding such equations took basically 30 years. Okay, so that was one of the big open problems that people had to overcome before one could go on and simulate black hole, dynamical black hole spacetimes in full generality, like black hole binary mergers. The second thing to bear in mind is that in these equations, in particular the lapse, you see that it appears with second derivatives. We will see later today that therefore, depending on what evolution equations you provide for the lapse and the shift, the choice of lapse and shift also contributes to the hyperbolicity of the system. So not only you have to be careful with the choice of coordinates to make sure that they do not develop singularities in the future, but that you need to make sure that they do not spoil the hyperbolicity of the system. Okay? And last but not least, it turns out that, as we shall see, well, I'm stating it here, this system of evolution equations is only weakly hyperbolic. And we'll see later today what weakly hyperbolic means. And the main problem comes basically from this term. So this term has second derivatives of the metric, and the combinations are just the wrong ones to give you a hyperbolic system. Okay, and understanding this was one of the other stumbling blocks that people had to overcome to simulate black hole spacetimes. Okay, so this system is only weakly hyperbolic, so you cannot use it to evolve, say, black hole spacetimes.
What does it mean, weakly?
We'll explain it later today. It's all right. So before we move on, there's one thing that we need to discuss, which is constraint preservation. So we can write the Einstein equations in the following way. So if we do decomposition using the normal vector to the hypersurfaces. We can write them in this way, where this curly m is the momentum constraint and this curly h is the Hamiltonian constraint. So remember that the normal projection of the Einstein equations gave us the Hamiltonian constraint, the normal tangential projection gave us the momentum constraint, and the tangential projection gave us the evolution equation for the extrinsic curvature, right? That's what I show here. Now one can show that if you now take the divergence of this equation, okay, now this is 0, right? Because the Einstein tensor is by the Bianchi identity has 0 divergence, and the stress tensor is also conserved, so that's equal to 0. So now you've got an equation which gives you, well, you've got this equation now. And if you now consider the projections of this equation, the normal projection of this equation gives you an evolution equation for the Hamiltonian constraint, which has this form. Some operator. So that's the normal projection of this equation, and the tangential projection of this equation gives you an evolution equation for the momentum constraint. So notice that this is a time derivative, right? Because that vector has d by dt. So when you do, so that's a time derivative. Does everyone see that this is a time derivative? Okay, so that's an evolution equation for the momentum Hamiltonian constraint, and the tangential projection gives an evolution equation for the momentum constraint, which has basically the same structure. And these are terms. So these L's are just terms that are homogeneous in the Hamiltonian constraint and momentum constraint. Okay, they're not important. The only thing that matters is that they're homogeneous. So what does this tell us? So these equations tells us that if the constraints are satisfied initially, okay, and we satisfy the Einstein equations. So if you satisfy the Einstein equations, these two terms vanish. So if you satisfy the Einstein equations, then you have an equation which is a linear equation for the constraint with 0 initial data. So this guarantees that the constraints will continue to vanish in the future. So if the Hamiltonian constraint at t equals 0 and the momentum constraint at t equals 0 vanish, and we satisfy the Einstein equations, then at all times. Okay? So that's important. So this is basically the strategy that one uses in numerical relativity and what is called free evolution. So what we do is we satisfy the constraints initially, and then we just evolve the evolution equation, just solve the Einstein equations, and this guarantees that the constraints will continue to vanish to the future. So we'll continue to solve the Einstein equations to the future. Okay? That's what we have to do when we do numerical evolution, basically because the constraints, both the Hamiltonian and momentum constraints, they are elliptic equations. And elliptic equations are expensive to solve. So doing it in practice and in full generality on each hypersurface, solving the constraint, which is something you could do, and then the fact that the ADM evolution equations are only weakly hyperbolic shouldn't matter, it's not doable in practice because that's just too expensive. Elliptic equations are expensive to solve computationally. But the fact that the constraints satisfy these evolution equations then allows us to just worry about the constraints initially, and then we don't have to, well, in practice you monitor the constraints, and this tells you how well you are solving the Einstein equations. That's something you always have to do in numerics, because when you discretize the equations you will inevitably make errors, the truncation errors, and therefore you will never satisfy the constraints exactly. Okay, so we monitor how well we satisfy the constraint. Okay, any questions so far? Okay, then in the rest, then I will change gears and I'll discuss another formulation of the Einstein equations, which is not weakly hyperbolic, which is in fact strongly hyperbolic, and that's the generalized harmonic formulation.
What are the typical initial conditions that we use?
There are techniques to construct initial data, for example, corresponding to two black holes with intrinsic spins and momentum that orbit around each other on a quasi-circular orbit. So that's something that can be constructed, and this requires a bit of fine-tuning, but there are there's open sets of initial conditions corresponding to sort of physically motivated or realistic situations. That said, constructing one of the issues, because if you have, say, two black holes orbiting each other, that's the kind of initial conditions you would be interested in if you want to sort of do some simulations for LIGO. Then the problem is that this is not a stationary configuration, right? It has to have gravitational waves, right? And one of the main issues is to find suitable variables that satisfy elliptic equations that minimize the amount of initial radiation that you have to have when you have these sort of binaries. So that's still an open problem. So in the sort of most standard way of constructing initial data has a certain amount of initial radiation, well, that's something which you usually discard. So when you start the simulation, there's always an initial burst of radiation. You ignore it, and then you find two black holes that just quickly go into a circular binary. Yeah, and when in the next lecture we discuss BSSN, which is a strongly hyperbolic formulation, we will see that we do conformal transformation of the metric, and the singularities are hidden in the conformal factor and the rest of the variables. So that you write elliptic equations for the conformal factor. Yeah. Okay. So let's go generalized harmonic coordinates, GHC. All right. So let's start again with the Einstein equations. And now I will write them in the trace reversed form. So, the Einstein tensor. So you have is Ricci (8 by TAB), and that's the same thing. You just take the trace and trade the trace of the Ricci by the trace of the stress energy tensor. You get the trace reverse version of the Einstein equations. Okay, that's just it's just the same. So to see what generalized harmonic coordinates do for you, it's useful to write the Ricci tensor in terms of the Christoffel symbols and their derivatives. Okay. So So the idea of generalized harmonic coordinates is that one prescribes wave equations for the space-time coordinates. So one chooses, it's a choice of coordinates. So we choose our coordinates such that they satisfy, so that's the scalar D'Alembertian. So we treat the space-time coordinates as scalars, and we prescribe a wave-like equation for them. And that's the same as, let me see. And we say that they satisfy this evolution equation with some unspecified source functions. So here the indices run from, say, 0 to d, so they are d plus 1 indices, right? So the choice of source functions is parameterizes the choice of coordinates, right? Because that equation uniquely determines the evolution of the space-time coordinate. Okay, so if you choose certain source functions, then that determines the coordinates. So it turns out that these coordinates are suitable to evolve black hole spacetimes. Okay? And if you set the right-hand side to 0, then these are harmonic coordinates. Now, what does this buy you? If you now, given that this, basically, this equation restricts the first derivatives of the metric in this form, okay, then if you define, you can define, well, then what you can do is you can trade derivatives of the Christoffels by derivatives of the source functions. Okay? So making this choice of coordinates, then the Ricci is the same as the following. Okay? And so in these coordinates, the Einstein equations look like this. Now, in order to close the system, one needs to provide an evolution equation for the, let's say, source functions of this form. Now, and this can be a linear, this can be an operator that depends on the metric and its first derivatives, but not on the second derivatives of the metric. And this can be anything. So that's, again, your choice of coordinates. So what does this buy you?
Sorry, what do you mean by first derivatives of the coordinates or the metric?
Of the metric.
Yeah.
So what does this buy you? In the second part of today's lectures, we'll study hyperbolicity. But what this buys you is that this equation for the metric is nothing but a nonlinear wave equation. So it's manifestly hyperbolic, it has no issues with that, and you can just solve it straightforwardly using standard techniques. Okay? And you can see how simple this equation is. Okay? The difficulty here is in finding suitable source functions, but I just told you that harmonic coordinates are just fine. So if you choose harmonic coordinates, then all these terms are 0, and there's nothing to evolve. This feels like magic, but it is not. And in fact, Madame Choquet-Bruat proved in the 50s so she proved in the 50s that if the constraints, which now in this formulation are, if you want, are satisfied, and furthermore, that the time derivative of this equation at t equals 0 is 0, then at all times. Okay? So it means that if you make this choice of harmonic coordinates initially, and you ensure that this time derivative of this equation vanishes, then this is true at all times. And the reason why this happens is because using the Bianchi identities, you can show that the constraints satisfy a homogeneous wave equation of this form. Right? So since this is just a wave equation and a homogeneous wave equation, and if you have 0 initial data, then the fact that this is a wave equation guarantees that this is 0 at all times. This is slightly more non-trivial because, as you can see, that's the space-time Ricci. So this equation is coupled to the Einstein equation, and showing that this is true is sort of is non-trivial, but that's basically the logic. So you have a wave equation for the constraints with 0 initial data, so then this is guaranteed to remain 0 at all times. So I just say that Madame Choquet-Bruat, still alive. She's like 100 years old, or 102 or something like that. And I think she is, I think there was this conference in 2015 to celebrate the 100 years of general relativity. And at the time, she was one of the 3 people alive that had a scientific interaction with Einstein. So she actually knew Einstein. And yeah, so she tells the story that she was at the institute in the 50s working on this, on showing that the initial value problem for general relativity is well posed. And she went to talk to Einstein, and apparently he wasn't too interested. But anyway, so just one last comment about this is that these constraints, these you can show, and I'm not going to do it, this is equivalent so this you can show that this is equivalent to the Hamiltonian and momentum constraints being 0 at time 0. Okay, so what do we do in practice? So if you expand this, so remember that these are just the first derivatives of the Christoffel, of the metric, because that's the Christoffels. So that gives you, so you make, in practice what you do, you make a choice of coordinates. So this fixes some of the metric components if you want, and that gives you some of the time derivatives. So in practice, yeah, all I want to say is that in practice you solve the constraints as you would normally do if you wanted to do ADM type evolution, and from these you read off what conditions, what initial conditions on the sort of space-time metric functions you have, and together with this, because of course this is a wave equation for the metric, for the space-time metric. So you have to provide initial data for the metric, for the full space-time metric, and the time derivatives, right? And those are not free, so this fixes some of the time derivatives of the metric components. So not all time derivatives are free, just in the same way that in the ADM formulation, the induced metric and the eccentric curvature are not completely free. They have to satisfy the constraints. So it's the same here. The caveat with generalized harmonic coordinates or harmonic coordinates is that, of course, they penetrate horizon, so they cover the interior of black holes, but at the interior of black hole there's a singularity where the theory and the coordinates, everything breaks down. So to get it to work in practice, one has to do excision. So it means that as part of your evolution scheme, you have to locate apparent horizons, so that's a relatively easy thing to do, and then you need to excise the interior of black holes. So that's conceptually straightforward, but computationally it's not so straightforward. Okay, but that's the sort of one of the caveats of this implementation. And we will see that with ADM type formulations, then you can choose coordinates such that they do not break down in the interior of black holes. So that's an advantage. There was a question.
So fixing CA to 0 is like choosing Laplace shift functions?
Yeah, basically. Yeah, you can think about that, yes. Any other questions? Okay, so to finish this part, I'll just state a theorem that tells us that the initial value problem in general relativity is well posed in a more precise way, and that's so the first theorem of this kind was proven by Madame Choquet-Brouat in the 50s, but then this was later improved by Madame Choquet-Brouat and Guéroche in the 60s. I don't know, it's 69. And this says the following. It says, let a hypersurface sigma with induced metric gamma. So the way you understand this is that you have a hypersurface, and on this hypersurface you have two pieces of geometric data. That's the first fundamental form, which is the induced metric, and the second fundamental form, which is extrinsic curvature. And what this theorem tells us is that these are not just data on this hypersurface, but these are really the pullback of the full spacetime metric onto sigma, and this is the extrinsic curvature. So this is just part of spacetime. Okay, so let this be initial data. Satisfying the constraints okay. Then this theorem tells us that then there exists a unique asymptotically spacetime mg, which is called the maximal Cauchy development of the initial data. Okay, such that three things. Mg solves the Einstein equations in vacuum, let's say. The Einstein vacuum evolution equations. 2, mg is globally hyperbolic. is globally hyperbolic. With sigma a Cauchy surface, gamma is the induced metric, is induced metric on sigma, and is the extrinsic curvature. Okay, so this is what I was saying earlier, that these data are the induced metric is the pullback of the full spacetime metric on this surface. And for any other spacetime satisfying these properties 1, 2, and 3 is isometric to a subset of n. Okay, so this is what it means for the Einstein for the initial value problem to well-posed in general relativity. Okay, so given its initial data, there exists a maximal Cauchy development, and any other spacetime satisfying the same initial conditions must be a subset. It must be isometric to a subset of this maximal Cauchy development. Then there are several things to bear in mind here. So this tells us that indeed that the Einstein equations are predictive. Okay, because given some initial data, you uniquely determine the future evolution of this initial data that gives you this space-time. So indeed the Einstein equations have the required predictive power that we demand that any physical classical theory has. But there's a caveat that this theorem, again, guarantees that solutions exist and are unique up to diffeomorphisms, but this only gives us short-time existence, right? Because the Einstein equations are nonlinear equations, so in general, one would expect that singularity is form. Okay, so this only gives us short-time existence. That's all you can prove. Global existence of solutions, that's a much harder problem for nonlinear equations. So there are very few results in general relativity that give you global existence. So for example, the two famous ones are nonlinear stability of the zeta space that was proven by Friedrich in the 80s, and the monumental work of Christodoulou and Kleinemann that proved global existence of nonlinear stability of Minkowski space. That gives you global existence of spacetimes which are near Minkowski for arbitrarily long times. Okay, but that's exceptional. Yes?
But in Christodoulou and Kleinemann result, they kind of have an additional restrictions on initial data.
Yes,
like
indeed.
You can't have like
absolutely
initial energy.
It has to be small. Has to be suitably close to Minkowski.
It's
and
not like small. It should be like suitably dilute.
Yeah, it's nonlinear stability, so it has to be it's small data result. So it has to be close to Minkowski, and it has to decay in a certain way so that you don't mess up with the structure of null infinity and so on and so forth. But proving that takes 500 pages, right? So I just want to emphasize that that global existence is very hard to prove for nonlinear equations. So this theorems, and the ones I'm going to state shortly about well-posedness and hyperbolicity only give you short time existence and uniqueness. Okay, and again, in general relativity, Penrose's singularity theorems tells us that indeed singularities do occur generically. So you should expect the space-time to end somehow. So this theorem again shows that the Einstein equations have the required predictive power. So, but singularities form, then this is where, and so if you see that this was formulated in late 60s, that's as a consequence of this is what sort of got Penrose to think about the weak and strong cosmic censorship conjectures, which are basically to guarantee that the Einstein equations continue to have predictive power in light of the fact that singularities form and form generically. Okay, and there are two separate situations where this can happen, and these are basically the two conjectures. The strong cosmic censorship conjecture relates to the Cauchy horizons. Cauchy horizons, remember in the previous lecture, are just the boundary of the region that you can predict uniquely from the initial data. And the strong cosmic censorship conjecture tells us that Cauchy horizons are singular, so you cannot go beyond. And on the other hand, the weak cosmic censorship conjecture relates to the structure of non-infinity. So the weak cosmic, in a sort of, let's say, in a rough sense, the weak cosmic censorship conjecture states that all singularities in GR must be inside black holes. Okay? So that infinite, so far away from any source, all spacetimes look near-Minkowski. That's what weak cosmic censorship conjecture says. And the two conjectures are independent of each other, so proving one does tell you nothing about the other one. Okay, and they are still open. Okay, so any questions about this? Then now we will change gears and I will discuss the notions of hyperbolicity, and I'll try to address Damian's question about weak and strong hyperbolicity. Okay? Okay, so we start with a definition of what it means to an initial value problem to be well posed. And for the rest of today, I'm not going to refer to the general relativity. So that's what I'm going to discuss, and it's just valid for any sort of wave-like equation. Okay? So we say that an initial value problem is well posed if three things happen. The system of PDEs there's a solution. The solutions exist. Has a solution, has a unique solution, subject to suitable initial conditions, Okay, so solutions must exist and they must be unique. Second, the solution depends continuously on the initial data. And 3, so the variation of the initial data outside a closed set closed set Fs of the initial hypersurface leave the solution unchanged in the future domain of dependence of S. Okay, so what do these conditions mean? So the first condition, as I said, is that there have to be solutions to the equations that we want to solve, and they must be unique. The second condition is that the solution depends continuously on the initial data. This is a physical requirement because if you think about, like for example, doing an experiment and setting up your system, you cannot in general, you cannot sort of tune your parameters of your system initially infinitely accurately, right? So there will always be some like errors. So what this condition tells us is that small changes in the initial conditions produce small changes in the solution. Okay, and that's a physical requirement, again related to predictivity. And the third condition, what this tells us is that there must be a finite speed of propagation, right? Because if you change the solution far away, then the region which is not causally connected to that where we change the initial data, then the solution should still be the same. Okay, so these are what these three conditions mean. And as I said, these for nonlinear equations, this existence is only short time existence. Now another question here is suitable initial data. So in this context, suitable initial conditions means that the initial data must live in an acceptable functional space of suitable regularity. So for example, if analyticity is not good, because so if you have an analytic solution, then you only need information at a point to determine the solution everywhere. So analyticity is somewhat at odds with finite speed of propagation. Right? So here, usually, the initial data has to be, say, I don't know, in L2 or in a suitable Sobolev space of regularity. So certain number of derivatives must exist, but not analytic. Okay? And then, given the suitable initial data, then the solution, we want the solution to also remain in analogous, in the same functional space. Right? So we want the regularity to be determined by the regularity of the initial conditions, basically. Okay? And not, and yeah, as I said, analytic is not good. Also because one can show, in general, that solutions to hyperbolic PDEs are not analytic. So you can find analytic solutions, of course, but generic solutions are not analytic. Okay? You can find more general solutions, in other words, which have low regularity. And just want to emphasize the point that analytic analyticity is not compatible with finite speed of propagation. Okay. Yeah, we can just get going. Any questions about this definition of well-posedness?
So according to the second condition,
yes.
does it mean that the chaotic system is not?
No, the chaotic system also depends on the initial data. It's just like chaos is something that happens at late times. So this is like short time. Yeah, chaos happens at, so even for chaotic systems, you have continuous dependence of initial data. On the initial data. Okay. Any other questions? Very good. So we will be considering. Yes.
Okay, I understand that this is all for classical systems.
Yes, indeed.
For quantum systems, the third condition might not be satisfied.
Yeah. Yeah. So it's all classical. Absolutely, yes. Yes. And this is why Einstein himself had serious difficulties in accepting quantum mechanics. So one can think of general relativity as the culmination of classical physics, as the sort of most advanced sort of classical theory. Okay. So so we'll start by considering first order equations. So consider an equation of the form okay, with this initial data, and a constant, and say n by n matrices. So if you think of U as a vector, n-dimensional vector of all the fields that we're interested in, and we just take these are therefore matrices, and we just take them to be constant for the time being, okay? And we will see that basically all nonlinear systems locally can be put into this form, okay? So we'll first start analyzing under which conditions one can find solutions to this linear problem, okay? A formal solution to this equation can be found by considering the spatial Fourier transform. So if you take the spatial Fourier transform, okay? Take the spatial Fourier transform, and you plug this into this equation, then you find that this spatial Fourier transform satisfies this equation. And again, here we are assuming that this matrix A is invertible. Okay? So now you can straightforwardly construct a formal solution to the system. So if you define a new matrix, curly A, as Okay? Then you can solve this equation by just exponentiating. And okay, and that's just the special Fourier transform of the initial data. Okay, so that's just a formal solution, just solving that linear equation. And once you have this, the solution for the special Fourier transform, then you take the inverse Fourier transform and you construct a solution to the initial problem. So from this, you get a formal solution by just taking the inverse Fourier transform. Okay, and I've called this a formal solution because it's not at all clear that this integral converges. Yes?
I'm sorry, is this matrices like purely M commuting?
Sorry?
Are these matrices commuting at different values of psi?
I don't think that this matters. Why?
Because then you need to use something like plus order exponent if you want to solve a matrix equation.
I mean, that's just I don't think there's anything to do with this commuting. I don't think there's any problem in writing the formal solution in this way. But the point is that this is a formal solution in the sense that this integral need not converge, right? It depends on how this exponent here, how this matrix behaves for large wave numbers. Okay? So that's the issue with this. So in order to be able to construct a solution, we need to have suitable conditions on how this matrix behaves for large wave numbers. Okay? And I'm just going to state this condition. Just keep this here. So one can show that a sufficient condition for the existence of this integral is that this exponential is bounded by some constant where this is positive and this is real. And okay, so sufficient condition is that you can bound this matrix in this way by constant for all n x naught greater than 0. Okay, so if this condition is satisfied, then one can show that the solution at any time, so remember x includes time, is bounded by this constant and initial data. So in particular, if the initial data is in L2, then the solution at late times is also in L2. Okay? So if And yeah, so if this is true, then that's a requirement for well-posedness. Well, that's what we'll take here as a requirement for well-posedness. If you have this, then you can prove existence, uniqueness, and all of that. Okay? So this tells us that at all late times, we can bound the solution from the initial data. And at late times, at any time, the solution cannot grow faster than exponential. Okay? That's a requirement of well-posedness. And let me just give me 2 minutes, and then we take a break, and we continue with this well-posedness.
Sorry, why do we want to expand?
Huh?
Why should be increased?
That's a minimum requirement you need to prove that that integral converges.
So that we don't have singularities for a finite time?
Well, yes, yes, if you want. So that basically means that the solution doesn't grow too fast. And the point is that this is independent of the wave number, right? So for example, in many systems which are ill-posed, then you find that the bounds you have here depend on the wave numbers, and then that basically forbids the integral from convergence. So the point is that you can bound this. The bound you get here is independent of the wave numbers. Yeah, so in many cases when you want to show that the system is, I'm just jumping ahead, but basically this matrix here is what we will call the principal symbol. And this tells you that this principal symbol as a function of the wave numbers cannot grow too fast. And for ill-posed systems, then that's basically where things break down. And in particular for ADM, that's what happens. So all of this is equivalent. So this boundedness condition, is equivalent if anyone, by the way, if anyone is interested in the mathematical details of all these proofs, just ask me later and I'll give you the reference of the book where you can find all these proofs. But we don't have time to do this here, okay? So it's not that this is, yeah, you can prove all of these statements. So it's equivalent. Is equivalent to the existence of a family of positive, definite, uniformly bounded Hermitian matrices which I'll call it curly K, such that sorry, okay, so that they bound these matrix curly M and themselves are uniformly bounded by a constant lambda, and that's the identity matrix and that's true for all wave numbers. Okay, you can see that the two conditions are the same, are equivalent, and what this allows you, so these matrices curly K, they are called symmetrizers. That's a so-called symmetrizer. And what this allows you to do is to define an inner product, and with this inner product you can bound the solution. So as you can see, the whole point of well-posedness is that what well-posedness gives you is a bound on the growth of the solution in terms of the initial data, and you don't want the solution to grow too fast. Okay, that's what well-posedness means basically. And too fast, not too fast means not faster than exponential. So with this, if you've got this matrix, if you've got the symmetrizer, you can define an inner product in Fourier space. I think I probably forgot. Yeah, I'm not sure about this. I think this may not be quite right. Maybe like this. So you can define an inner product okay. If you define this inner product, then these conditions here allow you to come up with, to bound the solution based on this inner product as a function of time, like this, in terms of the okay, that you can prove this. And again, and from this, what this gives you the mathematics literature, this is called an energy estimate, and to go from here to here you use something called Grunwald's inequality. But okay, so again, so this symmetrizer allows you to, again, bound the solution in terms of the size of the initial data, okay, which uses the same symmetrizer. And that's called an energy estimate. So it's basically the same condition. And the reason why I'm saying here is that we will go back and forth, and in some instances it turns out to be easier to prove well-posedness by finding a suitable symmetrizer rather than finding the explicit conditions on the principal symbol on these matrices. Okay, and I will state later that the conditions on this matrix on the principal part are equivalent to the existence of a symmetrizer. Okay, so let's take a break and then we'll continue from here. Okay, so far we've seen that well-posedness is about how this matrix curly M grows with the wave numbers. So in order to understand the behavior of this matrix for large wave numbers, it's useful to do the following. So we are interested in the large wave number behavior because that's what determines the convergence of the integral. So we define the following rescaled coordinate okay, so these now spatial psi have unit norm with respect to just the Euclidean metric, which is what we're considering now. Okay, and in terms of these variables, then the bounds that we had earlier say, the previous bounds, is, now it's not curly m, it's just standard m, and it depends on this. This has to be less than a constant, and m is the limit for large wave numbers of of this curly m. That's all that matters in terms of the bound that we wanted, and that's just minus the inverse matrix B. Okay? So, as you can see from here, all that matters in terms of well-posedness is just the part of the equation that has the derivatives. So this is just a first order equation, so that's this term in real space, that's the only term with derivative. Right? The constant term in the equation just doesn't matter in terms of well-posedness. So we call this m the principal part. And that's something that when we look at second order equations and so on, so the principal part is basically the terms in the equation with the highest derivatives. And the reason why these are the ones that matter is because when you take the Fourier transform, with the terms with the highest derivatives will give you the higher powers of the wave numbers, and it's for these large wave numbers is what you need to control. Okay? So all that matters in terms of well-posedness is the behavior of the highest derivative terms in the equation. Okay? One can prove the following. One can satisfy this bound. The bound can be satisfied if m has real eigenvalues Okay, so one condition that we will need to impose on the principal part is that it has real eigenvalues. But in addition, we'll need to impose that m is diagonalizable. So that's the other second condition. And the reason why this second condition matters is the following. So, like, if m is not diagonalizable, but it has a Jordan block of size m times m, okay, then one can show that this can grow like a polynomial. Okay, so then you cannot satisfy this bound. And the problem with that is that one can then still control the solution at late times in terms of the initial data, but in order to get rid of this polynomial growth, you need to take derivatives of the initial data. Right? So in this case, one can show that the solution at late times, say the L2 norm, you can prove a bound of this form Okay, so what this means is that the L2 norm of all derivatives up to order m. Okay, so you can still prove this, and this is an issue, because if your initial data is in a certain Sobolev space of say h, say k plus m. Okay, let me just. Then what this implies is the following. So if this means that if your initial data is in a Sobolev space of k plus m, which means that basically k plus m derivatives exist and are bounded, then what this inequality tells you is that the solution is only in hk. So there's a loss of derivatives. Okay, because you take m derivatives here. So this means that the solution at late times is less regular than the initial data. Okay, and while this is fine for linear systems, this is disastrous for nonlinear systems. And yeah. Because then you don't have enough control of the solution at late times. Then it doesn't allow you to prove energy estimates and decay and so on and so forth. And numerically, if you have these, then the solution will blow up exponentially fast, or faster than exponential, in fact. Which is in a way what this initial this condition tells you, that you have this term will basically be polynomial multiplying an exponential. So you have at the nonlinear level, you would have fast and exponential blow up. Okay, so now we can define what we mean by well-posedness. So well-posedness so we say that a system of this linear system is well-posed if m, the principal part, in terms of this unit vector, the principal of, so m is diagonalizable with real eigenvalues okay, so we call m principal part or principal symbol, and it's a term with the highest derivatives. And we say that a system is, sorry, that's well-posed. And if indeed m is diagonalizable and has real eigenvalues, then it means that you can decompose S in this form, where these are just the diagonal matrix of the eigenvalues, and this is the matrix of the column eigenvectors, and that's the, so you can write by similarity transformation, you can write M in this way, And from this, you can construct a symmetrizer by just considering this. Okay? So if this matrix is, again, is diagonalizable, has real eigenvalues, you can construct a symmetrizer in this way, which then has the right property. So in particular, then you can show that and it goes the other way around. So if you have a symmetrizer, you can show that this is diagonalizable. And if you find a symmetrizer which is Hermitian, is bounded, and all of that, then you can prove that it's diagonalizable and so on. Okay? So again, we call this the symmetrizer, and the reason why I brought this up is because in some instances it's easier to construct a symmetrizer rather than diagonalizing a matrix and finding its eigenvalues. So in particular, is the case for some complicated theories of gravity that we will I'll mention later, like for example Lovelock or Hortensky. Then it's much easier to prove well-posedness of a certain formulation. It's easy in that case to show that there exists a symmetrizer with these properties, and then the rest follows. So you don't have to construct explicitly the eigenvalues and so on, which can be difficult. Okay, so just to say that these two, the fact that this principal part is diagonalizable and has real eigenvalues is equivalent to the existence of the symmetrizer. Okay, so notions of hyperbolicity. So we say that PD is weakly hyperbolic if M has only real eigenvalues okay, and PD is strongly hyperbolic if M has a symmetrizer. Has a symmetrizer K that satisfies this property over here, and that is bounded. Okay, and strong hyperbolicity is sufficient for well-posedness for nonlinear equations. Weak hyperbolicity is not, and the ADM equations that we wrote earlier today are only weakly hyperbolic. And in the physics community, trying to do numerical evolutions of general relativity, for many years they just kept using the ADM formulation because that's very obvious and it's easy to implement. But these notions were not understood, so people just kept failing for like 30 years until Franz Pretorius used the generalized harmonic formulation, which is manifestly hyperbolic, and succeeded. And then it was only appreciated that strong hyperbolicity is key. And the other notion, the other formulation of the Einstein equations that we will see in the next lecture, which is called BSSN, has this property, but people realized that that was stable and things worked, but they had no understanding of why, and only later they realized that the reason why things worked was because that formulation is strongly hyperbolic. And we will see when we discuss it that it differs in an essential way with ADM. In particular, the principal part differs in an essential way. So what you do is just you change the two derivative structure of the equations. Again, so the principal part, well-posedness, cares about the highest derivative terms in the equations. Okay? Any questions so far? So in the rest of today's lectures, we'll see how nonlinear systems, second order up to second order in derivatives, which are relevant for general relativity and alternative theories of gravity, can be put in a first order form and then find and state the conditions that such system should satisfy so that they are well posed. And I should emphasize that well-posedness, as I said earlier today, is not independent of the choice of coordinates, because the gauge variables enter with two derivatives in the equations, so they contribute to the principal part. Okay? So the choice of coordinates is not completely free, if you want. Okay. Ooh. Okay. All right, so nonlinear first order equations. These are equations of this form. Where now these matrices depend on the coordinates and the fields, okay? And with initial data, okay, so one needs to assume that A is invertible at all times. So in a nonlinear system, then this may cease to be the case at late time, so that's when a singularity would form, for example. Right? The lack of invertibility of this matrix is what would signal the formation of a singularity. So in this case, one can write this system as before, with some B prime here. So this B prime is minus C prime. Okay, so now the principal part is what we would do to identify the principal part. We take the special Fourier transform and we consider the term with highest derivatives. In this case, they're only first derivatives, so the principal part would just be this term multiplied by the by the wave number. Okay, so the principal part is B prime that's the principal part. Okay, so now we just generalize all we said earlier to this case. So we now, the same statements I said earlier would apply, but now we require that there is special metric on our surfaces, so that this is unit norm. Okay, so now we would say that such a system is is strongly, the notions of hyperbolicity in this case would be the following. So we consider these vectors with unit norm with respect to arbitrary curved metric on the spatial hypersurfaces. Okay? Then we say that this is weakly hyperbolic if the principal part M has only real eigenvalues for such sigma. But now, and we say that it's strongly hyperbolic if it has real eigenvalues and is diagonalizable. Okay? And on top of that, we need to require that the eigenvalues and the eigenvectors depend smoothly on the wave numbers. Okay? And that's equivalent to their existing asymmetrizer, which has the same properties as stated before and is bounded.
But now the matrix B, the principal part, depends on the solution.
Yes, that's right. So these properties may fail, and that's when singularity would form. Right, so you need to assume, so in particular, as I said earlier, this whole construction assumes that this is invertible, and this may not be the case for all times, or for all initial conditions. Okay? So let T be an eigenvector of the principal part. Okay, so let be an eigenvector. So in this case, with eigenvalue and let me call it xi naught, and that's already suggestive of where we are going. So then, this implies that this eigenvector satisfies the following equation. Okay? And we can write this covariantly as okay. So I define this okay, I haven't done anything. So sometimes people refer to this as the principal part, because after all, there's this involves the coefficient of the time derivative, which is this matrix A, and the matrices of spatial derivatives, right? So it's the same order of derivatives. So that's also sometimes one refers to the principal part in this way. So this equation. So this is a matrix equation, okay? The indices which I have not written out explicitly is equal to 0. This can be satisfied for some eigenvector T, which is called polarization, okay? Only if the determinant of this matrix is 0. So, has non-trivial solutions. For some polarization T, if the determinant of this vanishes. Okay? So if that's the case, then we say that this wave, that this covector xi is characteristic. So characteristics tell us about the speed of propagation. So basically, the speed of propagation of a mode with this polarization is essentially the ratio between these two. So this tells you about the speed of propagation in the theory. So, summarizing, the principal part is just given by the highest derivative terms, and when you do the Fourier transform, if you solve this equation, this will tell you what the characteristic vectors are. This informs you about what are the speeds of propagation in the theory, and the eigenvectors of the principal part are the characteristic fields. So information propagates along characteristics. And one way to think about these characteristics is that these wave vectors, xi, they correspond to just plane waves of basically infinite frequency, because you just throw away all the other terms in the equation, and these are the only ones that survive. And these are basically plane wave-like solutions of the reduced system, which is, of course, is only valid when these wave numbers are large. Okay. And these notions will generalize to higher order equations and so on. Okay? All right. So let's consider now equations which let's consider also equations which are first order, nonlinear, but which are not quasi-linear on the special derivatives. So by this, what I mean is that equations of this form plus some nonlinear function of the fields and the special derivatives. Okay, so this can be a nonlinear function of the derivative as well. Okay, so in these cases and some initial data, okay, so for equations of this form, then hyperbolicity for these systems follows from looking at the principal part. And the principal part is, again, the terms with highest derivatives. And you obtain this by just taking the derivative of this nonlinear function with respect to the derivatives of the fields. So this depends on the IU and okay. So then one would look, then this will give you a matrix, and then one would look for the fact to the same conditions as before. One would demand that this has real eigenvalues and has a complete set of eigenvectors, or equivalently that there is a symmetrizer. Okay, so that's the principal part for this kind of equations. Same thing, just look at the highest derivative terms. And this is first order in time, but second order in space, for example, but non-linear. Okay, so that's for these kind of equations. And the reason why I'm mentioning this is because for, say, Lovelock or Hordensky type theories, then once you write them in a first order form, you get this kind of structure. So second order, let's look at now second order equations. So the general strategy to prove hyperbolicity of second order equations is to basically reduce it to a first order equation. And then we know what conditions we need to impose to the principal part of a first order equation so that it's strongly hyperbolic. And then when we will do the reduction and then identify the new principal part of the reduced first order system, and then from the conditions that this first order system has to satisfy, then we will obtain the conditions that the second order equation has to satisfy. So let's consider a general equation of this form. It depends on first derivatives and second derivatives. Okay, so the initial data up to second order is, and we need okay. So for equations of this form, the principal part is again the terms with highest derivatives or principal symbol. And let me just write the indices I, j is p I j mu mu is the derivative of the equation with respect to the highest derivative terms, which are second order. And we substitute the derivatives by wave numbers. Okay? So that would give us the principal part. And these you can write. Let me suppress the indices in this form. Okay, you just expand this, and A is when this mu and nu are both time derivatives, B when you've got a time and a space derivative, and the C is just a term with two. Okay. So this is the principal part, and okay, so now we have to restrict ourselves to a class of second order equations which are quasi-linear in the second time derivatives, but can be nonlinear, arbitrarily nonlinear in the second space derivatives, and that's the case for Lovelock or Hordensky. Okay, so we'll just consider a subclass of theories of second order equations, and I'll just take the conditions, and then I'll do the same for partially reduced systems, and then we'll be done. Oof. Okay, I'll finish the second order case, and next day when we discuss BSSN, I will state the conditions for systems which are like BSSN. Okay, so because it's already getting late. So we'll consider systems of this form. So these are systems which are quasi-linear in the second time derivatives, which means that the second time derivative appears linearly. So you can write the evolution equations in this form. Okay, so it's linear in the second time derivatives, but non-linear in all the other second derivatives and lower derivatives. So you can write the system as some new function x of everything else, which is just minus the inverse of this A times this one. Okay? And all these matrices depend on all these derivatives that you have here. So the idea now is to write this as a first order system. And since we know what the conditions are for first order systems, then we can then infer what the conditions are for the second order system. So that's basically the idea. So the first order reduction is that we introduce a new variable, b naught, which is just the time derivative of u, and the evolution equation. So first order reduction, I should say. We introduce a new variable, which is the time derivative, and special derivatives. Okay? So introduce these new variables, and the evolution equation for the special derivatives follows from the fact that this comes from the fact that the partials commute. Okay? The partial derivatives of u commute, so that gives us an evolution equation for the special derivatives, and the evolution equation for the time derivative is this. Okay, that's a first order system, and now there is a constraint. With a constraint, which let me call it curly C, is this constraint. Okay. From the evolution equations, it follows that if this constraint is satisfied initially, it will continue to be satisfied at late times. So that's fine. And I will state the result, and one can show that one can write. Let me just write this, and I'll state the result, and then if there are any questions, then we discuss it next lecture. Okay? So that's the setup. So it's clear we have done a first order reduction. So now what we do is we can write down now the principal part of this first order system. Okay? That's what we do. Let me write it here. And one can write the principal part of the first order system, and it will turns out that it takes a very simple form, where this so this part, because here we've got a vector, special vector, one chooses so that we can decompose the wave numbers so that they are, you can make a decomposition which is orthogonal and parallel to these to the wave number. So this part is the part which is orthogonal to the wave number. That doesn't matter for hyperbolicity. And then M, that's the only part that really cares, that the only thing you should care. And this this matrix M so these A's and B's are the matrices that I wrote initially. When we decompose the principal part, so that A is the principal part with two indices along the time direction. The B is the principal part of the second order equation with one space and one time direction. And the C is the principal part with two space directions. So the conditions on hyperbolicity for the second order system boil down to the usual conditions of hyperbolicity for this reduced matrix M. So you can show that the second order system is strongly hyperbolic if this matrix M is, has real eigenvalues and is diagonalizable. So I'm not going to prove this, it would take too long, but that's basically what. So hyperbolicity, strong hyperbolicity, bolicity follows from the usual conditions on M, where M is this reduced system. Okay? And in the next lecture, we'll see how another class of partially reduced systems, which partially reduced, meaning that they are first order in time, but second order in space, and that's the form of this BSSN formulation of general relativity, what the conditions of hyperbolicity are for such systems. Okay, so we'll leave it here today. Thank you.